So, I learned a lot in this class, but what I found most interesting was quantum mechanics. And I'm going to demonstrate a little bit of what I learned. On a quantum scale, everything acts differently. It behaves by a completely different set of rules. Take electrons, for example. This card here, the 9 of hearts. This is going to be our electron. Put it here on top of space. And I gave it a good few cuts. Let it get lost in space. Let it figure out where it wants to be. Now the weird thing about electrons, though, is that when nobody's observing them and when they don't have to choose, they have no idea where they are. They could be literally anywhere. Until, that is, you force them to choose, and it ends up right where it wants to be. Alright, so the chances of our electron being there on the bottom of the deck is about 1 in 52. That's excluding all the mathematics with how I shuffled, all that stuff I could never do. So we're going to try this again. The chances of our finding it on the bottom the first time was about 1 in 52. Chances of us finding it there a second time in a row is significantly less. Again, math. So, the thing is, that's exactly what electrons do, though. They take chances. I'm looking at my notes here on my laptop. I can't read my own writing, so I need this. They take chances. So, we know that electrons are particles, but that's only when we're looking. When we're not looking, when they don't have to choose where they are, they tend to behave more like a wave of probability, where you're more likely to find an electron in a place with higher probability than with lower probability. Makes sense. In a standard deck, the chances of finding one card in any given place is about 1 in 52. Again, math. So it's completely uniform throughout, which doesn't make it a perfect analog, but if you've got a better idea, just keep it yourself. I'm working here. So then, this would be our probability wave. If you can see that. Let me show you that again. If you can't see that, they're all 9 of hearts. Just take my word on that. Of course, that's our probability wave, until the electron is forced to decide where it is. So that's probability waves. Even cooler than that, though, is quantum entanglement. Occasionally, 2 cards can become quantumly entangled. And if you're curious, I'm just sorting this little packet into 2 smaller packets. So occasionally 2 particles can become quantumly entangled, so that no matter how far you take them from each other, they could be right next to each other or on the South Pole and on the Moon, doesn't matter. They remain connected. When 2 particles are connected like this, they share information between each other faster than the speed of light. So whatever you do to one affects the other. Let's test this theory. Here you can see I've got these 2 packets of cards. These 2 are quantumly entangled, so whatever I do to one will affect the other. Let's put that to the test. I'm going to use a special kind of shuffling for this. I'll take 3, flip over the packet and put it on top. I'll take 4, 5, flip it over, put it on top. And I'll do that completely randomly. And you can see I'm doing this completely at random. So now, if these two packets really are quantumly entangled, then whatever happened to this one should affect this one, and vice versa. So let's see. What are the top two cards? Boom! Both red 5s. So what's next? Black Queen? Oh, Black Queen. 2 red 8s. Black 10s. Black Aces. Black 4s. Red 4s. Black Kings. And red Queens. And that's quantum entanglement. So, that's cool and all, but how can we use quantum entanglement? What's it really useful for other than our own amusement? Well, how does teleportation sound? Because that's exactly what's being done with it. When two particles become quantum entangled, they share information faster than the speed of light, like I said. So theoretically, and in practice actually, if you introduce new information to one of these entangled particles, that information should be shared with the other particle and should create a duplicate. Let's see that in action. So here we have what we're going to use as a particle. It is a penny. See honest Abe? I'm not honest like Abe, I'm a magician. If I take the penny and I put it in my quantum teleportation paper, because yeah, I've got quantum teleportation paper. So I put this in my quantum teleportation paper. Gonna try and there, that'll work. And I fold that up, and then I introduce a quarter. I have fumbling fingers tonight. I introduce a quarter to my wrapped up penny. So, I introduce this new information, and let's see what has become of my penny. That shouldn't have happened, but you can see no pennies fell out. It's a quarter. The problem with that, though, is the original particle gets destroyed in the process. So you're not really duplicating anything. You're not teleporting anything, technically. You are destroying one particle and recreating it somewhere else. So no, you can't make money off of this. And that's just a little bit of what I learned, and I thought it was really interesting. Thanks.